Okay, so now that we know how to delete our nodes, what we're going to do is we're going to move on to analysis of our binary tree. And this is how we do things like finding or searching data and all that kind of stuff, or just displaying data. It all depends on what our goal is at the moment. So, get display list. This does what you would expect it to do. When it looks at a tree, it says, okay, what is the sorted what is the sorted arrangement of this tree? So if we have all this data, let me go back up for a second. Let's say on the left-hand side over here, I have that. I don't know if I remember the entire structure. We had we had 12, then we had 6, 8, 3, and then the other side we had 18 and 21, I believe. Just do a quick little connection here. Terrible arrow. Okay, so the get display list, what that's going to do is it's going to give us all of these numbers in a specific order. The most common order, which we call an in order, which means everything is in order, ascending order, you would actually see 3, 6, 8, 12, 18, and then 21, an in order. What it actually means, though, is that the root, or the parent, is in order with its children. So we don't get 3, 8, then 6. We get 3, and then the next in order number would be the 6, and then the 8. So do left child, do parent, do right child. Great. Seems fairly straightforward, right? But that's not the only form. So the term we use when we're talking about scanning a tree like this is called a traversal. Right? Whenever we're going to look at an entire tree, we're going to visit every single node of a tree, we call that a traversal. Now, the get display list does a special kind of traversal called a depth first traversal. It means it goes as deep as it possibly can, and then then it'll display the nodes or return the nodes in that order. So, or an in order traversal, which is what I meant. What it means is that the root is displayed in between its left and right children in order to give you a proper ascending order. There are other forms of traversals as well. There's a pre-order, which means the root gets displayed first and then the children, and then a post-order, which means the children and then the root. So this would be an in order, and then we'd have a pre-order, which means do the root first. The first thing we would see would be the 12. Then we would get its left child, which is going to be the 6. And then, because what happens is we start over here and it does itself, which is the 6. Then it's going to do its left child, which is going to be the 3. And then the 8. And then, of course, we go to the right-hand side now. So we're going to get the 18 and then the 21. It's no longer ascending order. The post order means that the children are always going to get put out there first. So not the 12, because it's got to do its child first. So it's going to do the left child. Oh, not the 6. It's got to do its children first. So we're going to see 3, then we're going to see 8, then we're going to see 6. Now we got to do the right side of 12, 18, but it's got to do its children first. So we're going to get 21, then we're going to get 18, and then we're going to get 12. So we can see it's all just a matter of what order things are visited in. And this could be used for various scenarios depending on what you're trying to do with your data. So as I said here, we can use the property of a binary tree that says smaller values are always on the left and larger values are always on the right. So this is actually a simple recursive function. So this idea of the in order, it means do the left child, then do the root, then do the right child. But if we look at this, this is a recursive function, which means this says do the left. So that means do this entire thing. Then do this one, then do this entire thing. But that means do this entire thing like it's all on its own. So that would say, okay, do the entire left, then do me, then do the entire right. So this is actually recursive functionality. What does it look like? Oops. First, say get display list of our current node dot get left. So whatever node. So if we're starting out at that root, it's going to say get display list of our left child, which is that entire thing, which is what I just said a second ago, right? And then once we've done that entire left child, do me. Okay, now do my right child. Okay, so you can see how this will actually work recursively. So imagine this. We say, okay, we come in, we see the first operation. It says, okay, do the left side. And that brings us down to the 6. But that one says, do the left side, which that brings us down to the 3. And that one says, do the left side. Oh, there is no left side. So then it goes to, okay, just do the 3, right? And then we're going to get that back up to the root, which is going to be the 6. And then it's say, do the right side. And then it comes back up to the 12. So left, root, left, node, right. Recursive. Now, in order to get the in order, pre-order, post-order, it's just a matter of reorganizing these 3 lines of code. You can see that we're outputting the current node in between the left and the right. If I want to do pre-order, that means just move this one above the left child. So we do the node, then left, then right. If we want to do post-order, we'd say left, right, then the node. Very simple. It's a very simple change, right? Just reorganizing the exact same logic. And recursion allows us to do that. We don't have to do any crazy changes or anything like that. Okay. So as it says, it will continually go left until it can't anymore. Display itself, then its parent, then repeat the process on the right child of the parent. All right. So here's a diagram just to show you. Let me just erase all this stuff over here. And we are going to paste this image in here, hopefully. We'll see if this works. Yeah, it does. So looking at this in-order, pre-order, post-order, we say, okay, we're at our tree, and we want to do an in-order traversal. That means do the left child, then the node itself, then the right child. So if we're looking at this, we start at the P. We don't output it yet. We got to go to the left child. Okay. We got to go to the left child. Oh, there's the B, because it doesn't have a left child, so we got to do itself. So we get the B. Then we go back up, and it's doing itself now, and now it's going to do its right child. But that one doesn't go because it has a left child. So it's always go as far as you can left, and then do itself. Go as far as you can right, and then do itself. And this process just continues. And we see the in-order, pre-order, post-order follows this exact same scenario that we said the whole time. Okay. One of the other operations that you may see sometimes when we're dealing with this is a mirror operation. It basically means literally flip everything. So all your lefts become your rights and your rights become your lefts. Like, wow, that must be really hard. How do you actually do this? Well, it's another recursive function. It's actually fairly straightforward. So mirror function that flips the left and right nodes from the root downward by level. So that means that the left node of P will become S, and the right node of P will be F. Okay, what's that actually mean? Well, looking at this picture here, we see our root node of 4, 2, 5, and then 1, 3, 6 by level. All we did here is literally swap. See, the 5 is still pointing to the 6. Okay, so that's very important. The only difference is the 5 is pointing to the 6 on the left side now. Basically, we kind of inadvertently switched the rule of the left and right being maximum or bigger or smaller. So that means that everything bigger is going on the left now, and everything smaller is going on the right. And we didn't actually have to enact that rule. It's actually a lot easier than that. All we're literally doing is saying, well, the left is now my right is now my left. That's it. So, again, this is a recursive subprogram that swaps the left and right children of a node, then calls mirror on each of those children. So imagine that. So the 4, we say, swap your children. So that means that it would look like this. So we have our 4, which points to 2, 5. And those point to other things. That's okay. But all we're really doing here is, actually, you know what? Let me write those in here. So this is 1, 3, and then on here we have a 6. We don't actually have anything for the left side of 5. So on the first step of this operation, that becomes 4 at the top still, because we're saying swap your children. We have 5, and then that still points to a 6 on the right. And then on the left, we have, on the right, we have 2, which is going to point to 1 and 3 still, because that's after one step of the recursion. So now the recursion says, now do the same thing to your children. So we just called swap on 4. We just called mirror on 4. Now let's call mirror on 5. Well, mirror says, okay, my left is going to become my right, and my right is going to become my left. So that means we have 4, which goes to 5, which now goes to 6 on the left, and nothing on the right. And then we do the same thing for the right child. We say, hey, 2, you mirror your children. 2 says, okay. So now my 3 is on my left, and my 1 is on the right. And that's all it is. So it's just do the flip, call mirror on each child. Do the flip, call mirror on each child. And when are you done? You're done when you have no children. You don't have anything to swap. That is the trick and the question here. What is your base case? No children. So the next one, I'm not going to go into a lot of detail on this because this is a much more complex topic, and I'm going to let you investigate yourself. This one is called get display tree levels. Now we had get display tree, which displayed either an in-order, pre-order, or post-order version of our tree traversal, right? What get display tree levels does is it displays everything by level and ascending order. So that means the get display tree levels would be P, and then F, and then S, and then B, H, R, Y, G, T, Z, W. Right? So it went by level. So we did P first, and then we did all of that level, and we did all of that level, all of that level, and then all of that level. So we could say the height of this tree is 1, 2, 3, 4, 5. And if we look at the levels here, make sure I get this all the way to the Y, and then the GTZ, and then the W. So those are our levels and how they're displayed, or how we would get them returned from that get display tree levels functionality. So this is often called what we call a breadth first traversal. We saw depth first traversal, which said go all the way to the bottom, give me the value. This one says, just go to the next level and give me them. So it's a little bit more complex because basically when you're looking at this, let's say we're at F and S and I want to do the breadth of the next level. Well, F has no connection to the children of S. So somehow we have to look at this and say, okay, how are we recursively breaking down the structure? And that's the part that I want you to investigate. So this is another function that returns a string for output. However, this time is not in order. It is by level from left to right, or ascending. This is much more work than it would first seem to be. You can get it done fairly quickly once you know the functionality behind it. Step number 1, determine the height of the tree. In this case, we know it's a height of 5. Step 2, for each level, display all the values on that level. So level 0, level 1, level 2, level 3, level 4. And this is called, as I said, a breadth first traversal. Now, simple little GIF shows you how this is actually working, but I showed you the exact same thing over here. Okay? Just let you watch this for a second before we move on. All right. Straightforward? Maybe. We'll see how well you did on that. So your practice work is to actually implement the functionality for the binary tree class, right? Which means you're going to have to create the node and everything like that. I put a demo program up on our class website, so you'll be able to follow along there and check everything else out you need to do. All right, good luck and have fun.